All right, let's go back to differential equations now. And we want to also get back to an application. So the application we're going to look at today is to cooling coffee, say. I brought water today instead of coffee. I had coffee this morning. I used to not like coffee, but you know, as people get older, they typically do. Although I do like cream in my coffee. I don't like it black. It's too acidic for me. Newton's law of cooling, say, for cooling coffee. Is there a Newton's law of heating as well? Well, let's wait and see. So we got a mug here. Got some coffee in there. Using a black pen. If you like black coffee, you can pretend that's black coffee. And it's cooling, right? You've brewed it, poured it in the mug. You're letting it cool because it's just too hot at first. Now, if you want to be extra precise about how coffee or any liquid cools, you'd want to take spatial effects into account, right? The heat has to diffuse through space and time and space. However, if you try to take spatial effects into account, you get what's called a partial differential equation. It's called the heat equation. And in this case, there would be a partial differential equation with partial derivatives, because there would be actually 4 independent variables: time, t, and 3 spatial variables, x, y, and z. It's more complicated. We don't want to be so complicated in this class. You would have to be more complicated if you want more accuracy, though. To not worry about the spatial effects, let's assume we've got a spoon in here. Here's my spoon. And you're stirring the coffee. Okay? Or maybe it's the thermometer and you're keeping track of the temperature and stirring at the same time. Hopefully the mercury doesn't leak out. So we're assuming that it's what's called well mixed. For fun, you got to humor yourself in some way. Let's call the temperature capital T. That'll be the temperature of the coffee at time little t. That'll be extra fun because then its rate of change, its derivative will be dt. What fun? D capital T, D little t. We should give units. Let's buck scientific standards and go with, say, in degrees Fahrenheit. Right? Scientifically, it's probably better to go in Kelvin or Celsius, but we'll go in degrees Fahrenheit. What would make the most sense for T? Probably minutes. I mean, seconds would be okay as well, but as far as like keeping track of the temperature of the coffee so that it cools to a temperature at which you could drink it, probably makes more sense to use minutes. Here's the model. The rate of change of the temperature with respect to time, dt, d capital T, d little t, is proportional to the difference between the coffee temperature and room temperature. Is it a good model? I hope it makes some intuitive sense. The bigger the difference, if the coffee starts out really, really hot, and hopefully doesn't boil away, maybe you got it inside a covered mug, but it's 500 degrees or something. Of course, if it's in a covered mug, it's going to cool very slowly. That difference is bigger, the rate of change is going to be bigger, in absolute value at least. If it's small, if it's almost room temperature, it's not going to change very fast. Proportionalities like this can be then converted to equations. In this case, a differential equation, because it involves the derivative of an unknown function. dt equals, leave some space. Over here to the right, let's write T minus the room temperature. Let's assume room temperature is 70. That's room temp. Why did I leave space there? Got a guess? Here's a little hint. You want to say, Michael? Yeah, we need a constant in proportionality, but that's what you were saying. We need something in front of here that's constant. If it's cooling coffee, dt is going to be negative, right? Graph of the temperature is going to be decreasing. Slope is going to be negative. But that's positive if it's cooling coffee. T is bigger than 70. So T minus 70 is positive. If I'm going to get the derivative to be negative, I need a negative constant of proportionality. Now, I could just call it K and say K is negative, but it's a bit more traditional to call it negative K, where K itself is positive. K positive, so negative K is negative. Actually, this model would work when the coffee is warming up as well. If the coffee is cool, maybe 40 degrees, room temperature is higher, 70, it'll warm up. This quantity will be negative. 40 minus 70 would be negative. And that quantity would be negative. Two negatives being multiplied gives you positive. The rate of change would be positive. The coffee would warm up. This is actually not just Newton's law of cooling, but Newton's law of heating as well. Actually, the more official name that includes both cases, I believe, is Newton's law of heating and cooling. It applies to both situations. What should we do? It's a differential equation. You should desire to solve it. The separation of variables work. That's really the only technique we know so far besides guessing. You might think because of the minus 70, it wouldn't work. Because remember on Monday, we had a few examples whether we were either adding or subtracting t. And I said you can't separate variables. However, 70 is a constant. It doesn't involve little t. You could divide both sides of this equation by capital T minus 70 and get all capital T's on the left after you also pretend you multiply both sides by d little t. Separate variables by pretending to multiply both sides by dt. That can be made rigorous. We did on Monday. And divide both sides by capital T minus 70. We would get d capital T over T minus 70. Just leave the negative k on the right side. It goes negative k d little t. Now you'd integrate. The right side, as it often is easy to do. Negative k is a constant, so I get negative kt plus an arbitrary integration constant, c, which I will call C1. Remember, K is fixed, but unknown. K would depend on what is cooling. Is it coffee? Is it pure water? Is it mercury? Hopefully not mercury. Don't drink mercury. Or something else. Formaldehyde. No, don't drink formaldehyde. The liquid itself determines what K is. It's related to, what's the official word for this? Thermal diffusivity or something like that. How fast does a liquid cool? It's related to that. We can integrate this one, not too hard either. Don't even have to bother with partial fractions. That integrates to natural log of the absolute value of T minus 70. And you might say having absolute value signs there is a good thing. You might argue that this then makes it apply to both cooling and heating. Cooling when T is bigger than 70 and heating when T is less than 70 as the initial condition. Plus C2, well, I'd subtract C2 from both sides, so I will not bother writing that. I would like to solve for capital T, so I want to get rid of the logarithm, so I will exponentiate both sides. Doing so gives the absolute value of T minus 70 to equal e to the negative kt plus C1, which you could, by a property of exponents, write like this. And then e to the C1 you could call C2. C2 is e to the C1. And then you could give a pseudo justification for getting rid of the absolute value signs by saying, you know, here C2 is positive because e to the C1 is positive. If I get rid of the absolute value signs, then I could call the constant could be positive or negative. I could call it C3. I think I'm just going to call it C. C e to the negative kt. You might say where C is plus or minus C2. That does seem to exclude the case, though, where C is 0. But C is 0 does work still. Add 70 to both sides. T is 70 plus C e to the negative kt. There is a general solution to the differential equation. But if this is going to be of any use, we need an initial condition to solve for C. And I guess we'd also need some other value of the temperature at some other time to solve for K. And then we might also wonder, is this model even really accurate? Again, you would need to assume you're stirring consistently. The only way to find out if it's accurate is to compare it against experiment. This could be, I don't know, a high school chemistry experiment. I don't know. Probably more middle school. Let's do the same thing we did on Monday and make the initial value of temperature be arbitrary. T sub 0 or T naught, like I said on Monday. Sometimes I'll say T sub 0, sometimes I'll say T0, sometimes I'll say T naught, just to remind you that people call it different things. And maybe I should give this thing a function name. Well, okay, let's solve for C first. I will give it a function name like before, but let's just solve for C first. E to the 0 is 1, so this becomes 70 plus C. Solve that equation for C by subtracting 70 from both sides, and you get C is the initial temperature, T naught, minus 70. And that can then get substituted into there. And now I'm going to use the function notation. So my unique solution of what I call a generic initial value problem, generic IVP, consisting of the differential equation and the initial condition that is arbitrary but fixed, is capital T equals, let's use phi for the function name, phi sub T0, that's the initial condition, of little t. Just write down this exact same formula, but replace C with T naught minus 70. 70 plus, in parentheses, T naught minus 70, e to the negative kt. If I imagine K to be fixed and T naught to be fixed, this is one function of little t. It is always a worthwhile thing to check that it works. And we've done this so often, including right now, that I'm thinking I'm probably going to put a checking problem on the final, where I give you a formula for a function and I say either check that it is a solution of the differential equation or not a solution. You should be able to do both. Usually we're checking things are solutions. And with the examples that we've done and will continue to do, you always check it in the same kind of way. You look back at the differential equation, left-hand side, right-hand side, substitute the function for the dependent variable, in this case, capital T. So the left-hand side, LHS, is d capital T, d little t. Substitute this phi function in there, meaning take its derivative with respect to little t. 70 differentiates to 0. The second term, when you differentiate it, is itself with an extra factor of negative k from the chain rule. The right-hand side, right there, negative k times in parentheses t minus 70, negative k times capital T minus 70, replace capital T, the dependent variable, with the function. That's always the most confusing thing for people. Replace the dependent variable, in this case, capital T. In other examples on Monday, it was y. Replace it with the function. Then simplify. Does it simplify to the same thing? There's the function. And don't forget to subtract 70. And it does simplify nicely. The 70s cancel there and there. This simplifies to negative k times, in parentheses, t naught minus 70 e to the negative kt. The exact same thing that you see here. These are the same. I could get rid of the 0 there and put the negative k in front. These are the same function of t. We are happy it's a solution. I wrote same there. I think I wrote match other times. There's a match. That's enough to mean it's a solution. If you did not get the same function of little t, it would mean it's not a solution. We should also check the initial condition. Phi sub t naught of 0 right there is 70 plus t naught minus 70 e to the 0. E to the 0 is 1. 70 plus t naught minus 70. The 70s cancel, leaving you with t naught. The initial value checks as well. A fundamental thing to be able to do when you're first learning about differential equations is checking solutions. So now, how would we use this? If we know the initial temperature, we can just plug it in there. We still got to figure out K though. Let's assume the initial temperature is, say, 130 degrees Fahrenheit. Is that too hot to drink? Oh, that's, I think, on the edge of too hot to drink. I probably would maybe still sip that, but if it was like 140, I probably wouldn't. Then your solution, if that is the case, is phi sub 130 of t. I'm replacing t naught with 130. And if I do that, in this formula, I get 130 minus 70 is 60. So I get 70 plus 60 e to the negative kt. Still, if we're going to use this, we got to know K. You need another data point. Let's assume that the temperature at time 1 is also known. Phi sub 130 of 1, let's pretend it's 125 degrees Fahrenheit. Is that realistic? I don't know. That second data point will allow us to solve for K. 125 will equal 70 plus 60 e to the negative k times 1. Replace little t with 1. Solve for k, you're going to need logarithms. You'll have to subtract 70 from both sides and then divide both sides by 60. You'll get e to the negative k is 125 minus 70 is 55. Divide that by 60. That reduces to 11/12. So negative k is the natural log of 11/12, which means k itself is the opposite of the natural log of 11/12. By a property of logarithms, that's actually the same as natural log of 12/11. In either case, it is a positive number. K is positive here. Negative natural log of 11/12 is a positive number, about 0.087, and natural log of 12/11 is the same number. Properties of logarithms there. This is about 0.087. Now let's use the model to say, for example, find little t so that capital T equals, oh, you waited too long, it's lukewarm, 75 degrees Fahrenheit. How long is it going to take until your coffee is just that because it's lukewarm? Use the formula again. We found K, use it. Capital T 75. Use the K we just found. 70 plus 60, this is an approximation here. 70 plus 60, K is positive, but I need a negative in front of it as the power of E. E to the negative 0.087 T. So I'm setting this equal to that, solve for little t. I'll need logarithms again, but first subtract 70 and then divide both sides by 60. This simplifies to 1/12. And that means take the log of both sides, divide by negative 0.087. T is 1 divided by negative 0.087 times the natural log of 1/12. You could also write that using properties of logarithms as 1 over positive 0.087 times the natural log of 12. Either answer is correct. They give the same thing, in fact. Natural log of 1 divided by 12, all divided by negative 0.087. It's about 28.6, as well as natural log of 12 divided by positive 0.087. Same thing. About 28.6 minutes. After time zero, after being 130 degrees. Of course, if you measured it to be 125 degrees after 1 minute, then you'd have to wait another 27.6 minutes. How accurate is this? It's hard to say for sure without comparing with experiment. But it must be fairly accurate because we teach it. And I think I did do an experiment actually about this with my daughter once when she was young. And yeah, it was approximately right. Just make sure to keep it stirred. In the last 10 minutes, let's confirm this with Euler's method. On Mathematica, though, because we're going to have to do a lot of steps. I am going to have you use Mathematica to do what I'm about to show you. So you will want to write it down, though I will share the notebook with you as well. Remember what Euler's method is. It's a recursive equations to generate sequences of approximate values of y, or in this case, approximate values of capital T. So I'm going to write down the formula, but I'm going to use capital T instead of y because that's the dependent variable. Capital T sub n would be the previous value of capital T, these are temperatures, plus the change in capital T, which came from the slope field, right? Using linear approximation, tangent lines to solutions based on the slope field interpretation. And the slope field had slopes equal to the right-hand side function evaluated in general at the previous time and the previous value of the dependent variable times delta t. Where that's a little t there, that's the step size. In time. You also have to update the times. So you actually have a second equation, little t sub n equals the previous value of time plus the change in time. So you use this a little on the assignment due today. You know, the textbook didn't really write these things down. They just argued intuitively and made a table right away. But I do want you to learn this and know it for the test and be able to implement it on Mathematica. To actually do that for the homework due Friday. But on the final exam, you should know the syntax. Now, the syntax is a little confusing. So listen carefully. First, I'm going to define my right-hand side function, my little f. Let me clear it first. It is just a function of capital T in our example. It's that, where k is what we found, 0.087. So when I type it into Mathematica, I can use just a capital T. In general, you might have to put a little t in there as well. It's my right-hand side function. K is 0.087. So I get negative 0.087 times t minus 70, capital T minus 70. Semicolon suppresses output. I also like to think of it as just a way to separate different lines of code here. This next part is the most confusing part. First, I'm going to set what delta t is. You can make a delta by doing escape, capital D, escape. There's a delta. Escape, capital D, escape makes a Greek letter capital delta. T. What should we pick? We have freedom in choosing delta t. Let's pick something reasonably small, like 0.1. Okay, here's the most confusing part. I am about to write down a function which is a function that I want to iterate in Mathematica to get the output for Euler's method, the t values, little t values, and in this case, the capital T values. In general, they might be y values. What name should I give to this function? Pretty much anything you want except f or t. I use a two-letter name. I typically do EM. Why EM? Because it stands for Euler's method. That's why. This is going to be a function that is going to implement these recursive equations. So I effectively need both of these. However, you do not want to use subscripts. I effectively want to type in these formulas without subscripts. You also want your input and your output to be two-dimensional, and therefore I'm using the curly braces that you see and using underscores like I've told you before when you're defining functions. The curly braces is essentially helping me define two-dimensional input and two-dimensional output. Little t plus delta t for the first thing that goes before the comma. Little t plus delta t. Oops. Delta is escape, capital D escape. And then for updating the value of capital T, do capital T plus the right-hand side function evaluated at capital T times delta T again. What I've got in these two spots are essentially the right-hand sides that you see here. For our example, which is autonomous, this thing simplifies to this for our example. You essentially have these right-hand sides without the subscripts. I also put little t first and capital T second. That's a choice. It's a choice that makes sense because the little t axis is going to be horizontal and the big T axis will be vertical. So you'd really want the first coordinate to be little t and the second to be capital T. So this is a function that I can apply to the Euler's method. For example, I could do EM 0, 130 to approximate the temperature at time 0.1. It's a little less than 130. Or I could use the function twice to approximate the temperature at time 0.2, 128.96. It's applying EM over and over again, that is implementing Euler's method. If I'm going to confirm the answer that I found a few minutes ago, for when the coffee will reach 28.75 degrees, we know the answer is 28.6 minutes. If delta T is 0.1, I better do like 286 steps or so of Euler's method. Really? 286 steps? There's 3 steps. That would be very cumbersome. The way to get Mathematica to do it quickly is with something called NestList. Capital N, capital L. Put the function name in there, put the initial condition, put the number of steps. Let's go out to 300 steps. NestList will apply the EM function over and over again, in fact, 300 times. With this initial condition, when little t is 0, capital T is 130. Will we get exactly 28.6 minutes again? Well, I know from section 1 that we don't, but we do get very close, it turns out, which is not necessarily to be expected because Euler's method is not a super accurate method. Though I do know why it worked out pretty closely this time. Enter this, we get a bunch of data points. And if you go down far enough, you eventually see the second coordinate become very close to 75. Right. Right here is one's closest, 28.4 minutes. It's going just below 75 by 28.5 minutes. Remember, the true answer is 28.6. So that did pretty well. Okay, so I will share this notebook with you after class. I will assign one thing where you need to use this kind of code. Just re-enter. All you need to do is change this function, change delta t if I ask you to change delta t, but then everything else is the same. Use NestList in the end. Okay, have a good day.